First, where your diagram fits. Your diagram fits in IP header, UDP header, stan attributes. This packet format is exactly what a stan message looks like. Turn RFC 5766 uses stan formatted messages for control, allocate, refresh, create permission, and also for one method of sending data. Turn send and data messages. These are stan indications, unauthenticated, packet structure, IP, UDP, stan header, stan attribute like zor-peer-address, stan attribute data. This is directly your diagram. Send or data method, always stan packets, always your diagram applies. The part turn client or server connection can be UDP, TCP, or TLS. This refers to the transport used between the turn client and turn server for control messages and also for relaying media. Turn can run over UDP over IPv4, TCP over IPv4, TCP over IPv4 with TLS, encrypted turn over TCP. This does not change the content of the stan header. It only changes whether these stan packets travel inside UDP, TCP, or TLS. Still stan, still your packet diagram, just different transport. Turn supports two methods for moving client to peer traffic. This is the most important part of the spec. Turn has two methods for sending relay data. Method 1, stan send or data messages, stan indications, uses full stan header, 20 bytes, additional stan attributes, very large overhead, 28 to 40 plus bytes, always unauthenticated, very flexible. This is what the diagram shows. Method 2, turn channels, uses a 4 byte minimal header, not stan, faster and lower latency, only works after creating a channel binding, limited to 16K channels, used by VoIP, WebRTC for media because overhead matters. Packet format, IP, UDP, channel data header 4 bytes, padded data, not a stan packet. It does not match your diagram, so it's minimal. It's a 4 byte minimal header compared to 20 byte stan. Let's connect this to the diagram. When the diagram applies stan binding request, stan binding response, turn allocate, turn refresh, turn create permission, turn send, turn data, everything above equals stan message 2, your diagram is correct. When your diagram does not apply, turn channel packets 4 byte header. So the diagram does just not apply to the channel data packets. Turn over TCP or TLS, stan is inside TCP stream, but packet layout changes. So the diagram does not apply to TCP, turn over TCP or TLS. Channel data looks like this. Channel number 16 bits, length 16 bits, then data. No stan header, no stan attributes. It's used for RTP, Opus Audio, VP8/VP9 video, DTLS, or SRTP media flows. So the channel data can be used for SRTP media flows or in LiveKit. Connecting to the questions, how does turn over UDP or TCP or TLS and how does it support two methods like stan send or data and channel data and channels and channel messages and the 16K channel. So here's the direct connection. Turn over UDP or TCP or TLS only affects the transport layer. Message is still stan. It matches the diagram exactly. Turn support two methods, stun, send or data. It matches the diagram. Method 2, channel data, 4 bytes. It does not match the diagram. Channels, a turn performance optimization. It replaces stun overhead. New header format, 4 bytes. Not compatible with stun layout. Channel messages use a small 4-byte header, 4 bytes instead of 20 bytes. Incompatible with stun, your diagram does not apply up to 16K channels. Each channel equal numeric ID. Bound to a peer, IP, port, allows scalable multi-peer VoIP. Visual comparison, super clear. Stun or turn, send or data, it matches the diagram. IP. UDP, stun header 20 bytes. Stun attributes, variable length. Turn channel data, it does not match the diagram. IP, UDP, channel header 4 bytes. Raw data. Why the spec uses both? Stun, send or data, header size 20 to 40 bytes. When used, signaling low volume data. Purpose, flexibility. Method, turn channel data, header size 4 bytes. When used, high rate traffic, RTP, VoIP, or video. Purpose, performance. So turns give you flexible messaging, stun, low latency data transport channels. In operation, the client makes a request to obtain an allocation using a turn-defined stun allocate method. So this goes hand in hand. The client makes a request, kind of like client to server. If successful, the server responds with a success indicator and the allocated relay transport address. A request might be denied if the client fails to provide adequate authentication to the server. The client must now send refresh message to keep the allocation alive. Allocation expire in 10 minutes if not refreshed. So the client, once allocated, does not stock up. It needs a refresh. So because the allocation expires in 10 minutes, unless the client included an alternate lifetime value encoded as a stun lifetime attribute. Unless the client actually requests for a lifetime allocation request. Allocation may be deleted by requesting an allocation with 0 lifetime. When an allocation expires, so do all of its associated channels. Allocations are represented using 5-tuple. At the client, the 5-tuple includes the client host transport address and port number, server transport address and port number, and the transport protocol used to communicate with the server. At the server, the same 5-tuple is used except the client's host transport address and port are replaced with its server reflexive address and port. An allocation may have 0 or more associated permissions to limit the patterns of connectivity that are permitted through the turn server. Each permission includes an IP address restriction such that only packets with the matching source address received in the turn server have their data payloads forwards to the corresponding client. Permissions are deleted if not refreshed within 5 minutes. So an allocation may have 0 or more associated permissions to it. So the patterns of connectivity that are permitted through the turn server. Each permission includes an IP address restriction. So it contains what IP it will restrict, that only packets with the matching source address received at the turn server have their data payloads forwarded to the corresponding client. Permissions are deleted if not refreshed within 5 minutes. Turn enhances the stun with 6 methods, 9 attributes, and 6 error response codes. This can be partitioned roughly into support for establishing and maintaining allocations, authentications, and manipulating channels. So these additional methods, attributes, and error response codes are to support and establish and in maintaining allocation, authentication, and manipulating channels. The 6 methods and their method numbers are as follows. Allocate number 3, refresh number 4, send number 6, data number 7, create permission number 8, channel bind 9. The first two establish and keep allocations alive. Send and data use stun messages. So the first two, the allocate and refresh, obviously keeps it alive. It will send it a refresh within 10 minutes and 5 minutes, and that's a request, client to server request. And send and data use stun messages to encapsulate data from client to server and vice versa. So it actually derived from stun messages to encapsulate the data from client to server. Create permission establishes or refresh a permission. So create permission method, again this is a message type, establish or refresh the connection from client to server, and channel bind associates a particular peer with a 16-bit channel number. This is how you kinda use the channel part. The error messages indicate the problems with turn features such as authentication failure or running out of resource. So in case that the client server authentication does not work, this method is what you will use. The 9 stun attributes, name, values, and purposes defined by turn are given in table 7.3. So these are the attributes. So it's not the message type, it's after the message type. The channel number, value 0x0000, purpose or use, indicates what channels associated data belongs to. Name, lifetime, value 0x000d, purpose or use, requested allocation timeout, seconds. Name, ZOR peer address, value 0x0012, purpose or use, appears address and port using ZOR encoding. Name, data, value 0x0013, purpose or use, holds data for a send or data indication. Name, ZOR relayed address, value 0x0016, purpose or use, server's address and port allocated for a client. Name, event port, value 0x0018, purpose or use, request that the relay transport addressing information use an event port, optionally request allocation of the next port in sequence. Requested transport, value 0x0019, purpose or use in a client to request that a specific transport be used informing the transport address. Values are drawn from the IPv4 protocol or IPv6 next hop header field values. Name, don't fragment, value 0x0001a, purpose or use, request that the server set the don't fragment bit in the IPv4 header in packets sent to peers. Name, reservation token, value 0x0022, purpose or use, unique identifier for a relay transport address held by the server. The value is provided to the client as a reference. So these are the diagram. IP packet, you have IP header, SRCIP, DSTIP, protocol equals UDP17. Then UDP datagram, UDP header, SRC port, DST port, length, checksum. Stun or turn message, stun header 20 bytes. You have type, length, magic cookie, transaction ID. That is the same for the client server request. Method or class, request plus response. Stun or turn attributes. So a stun and turn attributes is the same. The turn just extended. Type 16 bits, length 16 bits. Value padding, value counts a multiple of 4 bytes. Length bits as same as padding. Turn extensions, RFC5766. Type, name, purpose, 0x00c, channel number, purpose or use, we've discussed that. Type, 0x00000d, name, lifetime, and the purpose we also discussed that. And this is a unified diagram for oval or overall understanding. Let me just make it bigger. So we have an IP packet, IP header, SRC IP, DSTIP protocol equal UDP17 to UDP datagram. In UDP datagram, you have UDP header, SRC port, DST port, length, checksum. Then you have stan or turn message, and in that you have stan header with type, length, magic cookie, transaction ID, 96 bits. The 96 bits are used to match request or response, and the magic cookie. The length is equals to the total size of attributes. Remember, you can have multiple attributes on your message method, or on your request message or response. The type is the method plus class request or response. The stan or turn attributes, this is the length of the attributes you have in message type. Each attribute you have this type, length, value. We have type of 16 bits, length of 16 bits, value variable up to 64 kilobytes, padded to 32-bit boundary. Notes, value is padded to a 4-byte multiple, padding bits arbitrary. Length counts only the value, not padding. So the length in a message type, in this stan attributes only count the length in bits of the attribute, not the value or the padding. Remember, we pad it to make it easier for hardware to recognize it, and it is padded to 4-byte multiple. Turn extensions, RFC 5766. Turn method numbers, allocate, number 3, create allocation, refresh, number 4, keep allocation alive, send, client to server, encapsulated data, 7, server to client, encapsulated data, create permission. So this data is the response, right? Server to client, and this send is client to server. It's also encapsulated. Create allocation is allocate. When you see number 3 in turn extension method, therefore it is asking for allocation. Channel bind peer channel number. Turn attributes, type 0x000C, name, channel number, purpose 16-bit channel identifier, type 0x000D, name, lifetime, purpose allocation duration in seconds, type 0x0012, name, XOR peer address, purpose peer IP or port, type 0x0013, name, data, purpose payload for send or data, type 0x0016, name, XOR relayed address, purpose server assigned relayed IP or port, type 0x0018, name, event port, purpose request event port, optional pair, type 0x0019, name, requested transport, purpose UDP or TCP or SCTP, type 0x001A, name, don't fragment, purpose ask server to set DF bit, type 0x0022, name, reservation dash token, purpose token to associate paired ports. Additional concept, port numbers are separate per transport. TCP port space is not equal UDP port space, meaning TCP port 80 and UDP port 80 are different and can coexist on the same server. Servers using different transport protocols do not conflict. So that's what we discuss in how different protocol could have the same port number. So let's expand on this turn. Turn adds 6 new stan methods. These are the method numbers and functions. Method name, allocate. Method code 3, purpose, create allocation. It matches the stan diagram, yes. Method frame, refresh. Method code 4, purpose, extend allocation lifetime. Matches the stan diagram, yes. Method name, send. Method code 6, purpose, client to server to peer, stan indication. Matches your stan diagram, yes. Contains data attribute. Method name, data. Method code 7, purpose, server to client, stan indication. Matches stan diagram, yes, it contains data attribute. Method name, create permission. Method code 8, purpose, authorize a peer address. Matches your stan diagram, yes. Method name, channel bind. Method code 9, purpose, bind peer to channel number. Matches your stan diagram, yes, contains channel number. All 6 turn methods use stan packets. So the diagram is correct. All turn, control message, and send data. We have IP, UDP, stan header, stan attributes, turn attributes included. Turn adds 9 stan attributes. You listed them. So here's what each is for and when it appears. Attribute channel number hex 0x0000 C appears in channel bind purpose assign 16-bit channel. Attribute lifetime hex 0x000D appears in allocate/refresh purpose allocation lifetime. Attribute zor-peer-address hex 0x0012 appears in send or create permission purpose which peer to send to. Attribute data hex 0x0013 appears in send or data purpose encapsulated payload. Attribute zor related address hex 0x0016 appears in allocate response purpose your turn relay IP or port. Attribute even-port hex 0x0018 appears in allocate purpose as for even or paired ports. Attribute requested transport hex 0x0019 appears in allocate purpose usually 17 equal UDP. Attribute don't fragment hex 0x0001A appears in allocate IPv4 only purpose ask server to set DF bit. Attribute reservation token hex 0x0022 appears in allocate purpose token for port reservation. These attributes appear inside stan attributes block of the diagram. So the biggest clarification, there are two types of data packets in turn. Type A, send and data, stan formatted. It matches the diagram. IP, UDP, stan header, attribute zor peer address for send, attribute data, payload. Uses turn attributes, uses stan header, always matches the diagram. Used when low traffic flexibility needed. Type B, channel data, not stan, no attributes, only 4 bytes of turn header, then raw data. We have IP, UDP, channel number 16 bits, length 16 bits, then raw data. It does not use stan header, does not use stan attributes. The diagram does not apply here. It used for high rate media like RTP, VoIP, WebRTC. Channel data packet appears only after a channel bind method. So how turn methods work together? Step 1, allocate, client request relay, stan packet, requested transport, even port, etc. Step 2, create permission, authorize peer IP, port, then stan packet to zor peer address. Step 3A, send or data with stan header, or step 3V, channel bind peer to channel number. Stan packets to channel number, then step 4, channel data packets. Data with 4 byte, channel data header. Exactly how the diagram maps to turn. We have IP header, UDP header, stan header 20 bytes, stan attributes, type, length, value, padding. It applies to allocate, refresh, create permission, channel bind, stan binding, normal, turn send, turn data. It does not apply to channel data packets used for channel bind. Putting it all together visually, any turn method, allocate, refresh, create permission, channel bind. We have IP header, UDP header, stan header. The method for this is allocate or refresh. And then turn attributes. We have lifetime, channel, dash number, data, etc. Channel after channel data after channel bind. We have IP header, UDP header, channel header, 4 bytes, and raw data. So let's see the TCP ports. TCP ports and UDP ports are separate universe. Even though port numbers looks the same, 0 to 65535, TCP has its own set of ports and UDP has its own set of ports. They do not overlap. So TCP port 80 and UDP port 80 are two different ports, not the same. TCP port 3478 stan or turn over TCP UDP port 3478 stan over turn over UDP also totally separate. So why is this true? Because TCP and UDP are different transport layer protocols, each with its own connection tables and socket mapping inside the OS. The OS tracks sockets like TCP colon inside its SRC IP comma SRC port comma DST IP comma DST port. Then we have UDP inside it SRC IP comma SRC port comma DST IP comma DST port. They are separate structures in the kernel, so the OS see this as different. So we have TCP over 80 equals a TCP socket, UDP over 80 equal a UDP socket. Same number 80, but they are not the same port. The consequence, what your text says, two completely distinct servers can use the same port number and IP address as long as they use different transport protocols. This means you can run an HTTP server on TCP port 80, a QUIC or HTTP3 server on UDP port 80 on the same machine, same IP without conflict, and they will bind successfully. Like this code, server that bind 0.0.0 comma 80 comma protocol equals TCP, okay, and then server bind 0.0.0 comma 80 protocol equals UDP, then okay. This is exactly how HTTP3 is deployed. HTTP 1.1 and HTTP 2 use TCP 80 slash TCP 443. HTTP 3 QUIC uses UDP 443. Same port numbers, different protocol. Real examples where same IP plus same port is used by different protocols. Google and YouTube, TCP 443, HTTPS TLs, UDP 443, QUIC HTTP 3. Both hosted on the same servers. Both use for port 443, but one is TCP, the other is UDP. No conflict. Second, turn or stan servers. Other run UDP 3478, TCP 3478, TLS over TCP 5349, DTLS over UDP 5349, all on the same IP. DNS servers, UDP 53 equal normal DNS, TCP 53 equal large DNS responses. Zone transfer, same port number, different transport, no problem. Why your turn or stan understanding needs this? Turn has turn over UDP recommended, turn over TCP, turn over TLS, turn over DTLS. All these can use the same port number because they are different transport layer. This is what exactly the text means. The client or server connection has been specified for UDP or IPv4, TCP over IPv4, and TCP over IPv4 with TLS. So a turn server may run UDP 3478 to turn over UDP, TCP 3478 to turn over TCP, TCP 5349 to turn over TLS, UDP 5349 to turn over DTLS. All on same IP, same port numbers. Summary, simple. TCP port 80 is not equal UDP port 80. TCP port 443 is not equal UDP 443. They are separate universe. This allows HTTP 2 on TCP 443, HTTP 3 on UDP 443, turn over TCP 3478, turn over to UDP 3478, DNS on UDP 53, DNS on TCP 53. Same machine, no conflict. A turn request takes the form of a stan message whose message type is an allocation. So here is the message type is an allocation. Figure 7.12 shows an example. According to the stan long-term credential mechanism, the initial allocation request shown in figure 7.12 did not include authentication information. So it's rejected by the server. Here, allocate request, allocate error response, error code 401. The rejection is indicated by an allocation error response shown in figure 7.13. Here, allocate error. So a turn allocation error response includes the error code attribute with the value 401 unauthorized. The message is integrity protected and includes the realm and nonce attributes required by the client informing another authenticated allocation request. So don't worry, because this server actually provided a nonce and realm value that the client can use to be able to send a successful request. So in figure 7.12, we see a turn allocation request is a stun message. Here the protocol is stun. Using message type 0x0003, which is allocate request. This request also includes the requested dash transport and software attributes. So we have requested dash this is how you see the attributes below the type of allocate request. It does not include authentication information. According to stun long-term credentials, this request will fail. The error message in figure 7.13 provides the realm attribute via genie.ca and the nonce value the client requires to form its next request. So the realm attribute is actually the via genie.ca that the client can use for subsequent to make the response successful. The message also includes the message integrity attribute so that the client can check that the message has not been modified. So the message integrity shows that the message is not modified and the requested realm and nonce are correct. A subsequent request includes the username, nonce, and message integrity attributes. See figure 7.14. So here is the figure 7.13 with an error code unauthorized realm via genie. So as you can see, the response for this allocate response provide an error, but not just that, it also provide another attribute realm via genie.ca and a nonce and a message integrity that the client can use. So this is how attributes are being used by the client and the server. And this is the figure 7.14. So in the third, allocate request UDP user. So the user now enter its username because it requires by the server and the nonce that was provided to him. After receiving the request including the long-term credentials as shown in figure 7.14, the server computes its own version of the message integrity value and compares the result against the message integrity attribute value. If they match, this is sufficient information for this turn server to conclude that the client must be the appropriate server. It then permits the allocation and indicates the result of the request to the client that it is successful, like this. Allocate success response, and the attributes are ZOR relayed address to 16.49261 port and attribute fight ZOR relayed, and then it also have a bandwidth and lifetime of 60, etc. So a turn allocation success response, the message is integrity protected and includes the ZOR relayed address attribute, identifying the port and address allocated by the turn server. So because the message's integrity is protected, it provides an allocate response and includes the ZOR relayed address attribute. It identifies the port and allocated by the turn server to be then used by the client for this direct P2P. The allocation is deleted if not refreshed. The allocation request is successful as shown in figure 7.15 and the relay transport address is 216.146.46.55:49261. Note that Wiresharks perform the ZOR operation to display the decoded address. So Wireshark perform actually a ZOR to provide this decoded address. At this point, the client can proceed to use the turn server for relaying to peers. Once this is finished, The allocation can be removed about 4 seconds later. Packets 5 and 6 in figure 7.15 indicates that the client requests to remove the allocation. So as you can see, we have a lifetime here. So refresh request. After the request, the client requests to end this lifetime 0 with the username kfall, which is the same one who requested it. So the request is expressed as refresh with lifetime set to 0. So to actually uh, end that, you need to set the lifetime to 0. So that's how you can see that in real time in Wireshark. So the server responds with the success indicator and removes the allocation. As you can see in the frame 6, success response, lifetime 0 bandwidth. Note that the bandwidth attribute has been included in the allocation and refresh success indicators. This attribute, defined by a draft version of RFC 5766 but ultimately deprecated, was intended to hold the peak bandwidth in kilobytes per second permitted on the allocation. This attribute may be redefined in the future. As suggested previously, Turn has the advantage that traffic must be relayed through the Turn server, and this can lead to inefficient routing because you're now using the last part or the failover, i.e. the Turn server may be far away from a client and peer that are proximal. In addition, certain other traffic contents are not passed through from peer to client using Turn. This includes ICMP values, TTL. So these values are actually not included in Turn. So these are the restriction in Turn. So if you want to do this, you won't be able to do this in Turn. And IPDS field values. Also, a requesting Turn client must implement the STAN long-term credential mechanisms and have some form of login credentials or account assigned by the Turn server operator. This helps to avoid uncontrolled use of open Turn servers but create somewhat greater configuration. So how the text connects to the diagram. So the unified diagram now is how single turn or STAN message looks when it travels over the network. We have IP header, UDP header, STAN or turn header, 20 bytes, STAN or turn attributes. Everything, turn allocate, refresh, send data, ICE binding, channel bind, all ultimately get encoded inside that STAN or turn message structure. So the big idea is all turn and I signaling equals STAN messages with specific method plus attributes. These messages sit inside UDP, which sit inside IP. So the diagram visualizes the wire format. The long text explains the behavior and purpose of those messages. How message integrity check fits into the diagram. Text snippet. The server computes its own version of the message integrity value and compares the result against the message integrity attribute value. Where does this appear in the diagram? In attribute section as one of the STAN attributes. Inside we have STAN attributes. Type equal message integrity 0x0008, length equal 20, value equals 20 byte plus, HMAC SHA-1. This is how the Turn server verifies authentication. So this is the inside in message integrity. As you can see in this TLV, the value has a 20 byte HMAC SHA-1. Nothing about this changes the packet layout. It just means one of the attributes contains an HMAC. How allocate success fits the diagram. The relay transport address is 216.146.46.55:49261, displayed via ZOR relayed address attribute. In the diagram, we have attribute with type equals ZOR relayed address 0x0016, length equal 8, IPv4, value equals ZOR encoded IP plus port. Again, it's just another attribute. The diagrams, STAN or turn attributes, box is where these appear. Third, how turn methods fit the diagram. The text lists 6 turn methods. Allocate 3, refresh 4, send 6, data 7, create permission 8, channel bind 9. So where do they typically appear? Inside type field of the stun header. So we have stun header to type, to method, to client, request or response. This is the line in the diagram. Type method to class, request or response. So a turn allocate request is literally type equals 0x0003 allocate plus request class. This is how the server knows what kind of turn message you're sending. How turn attributes fit in the diagram. Turn introduces 9 attributes like XOR peer address, channel number, data, event dashboard, requested dash transport, etc. The diagram shows the structure for a generic stun attribute like attribute type 16 bits, length 16 bits, value. So turn simply defines new attribute types that fit into the same structure. So the diagram perfectly fits this. How channels, channel bind plus 4-byte header relate. Messages carried over channels use a smaller 4-byte header incompatible with stun messages. This is the one thing that does not follow the diagram. Channels bypass stun encoding. When channel mode is used, IP plus UDP plus 4-byte channel header plus raw data instead of IP plus UDP to stun header to stun attributes to data, meaning the diagram is accurate for allocate, refresh, create permission, send data, ICE checks, binding requests, but not for channel data packets. How ICE fits into the same diagram. ICE uses binding request, stun method equals 0x0001. These messages also follow the exact layout IP or the diagram exact layout IP to UDP to stun header to stun attributes. ICE specific attributes include priority, ICE controlling, ICE controlled, use candidate. These go into the stun attribute box. Example attributes type equal priority, length equal 4, value equal priority number. So ICE is just another set of stun messages using the same packet layout that the diagram show. How all this behavior map to your diagram. Authentication equal message integrity attribute in stun attribute section. Getting a relayed address, XOR relayed address attribute in stun attribute section. Creating permission, create permission method, method code 8 encoded in stun header. Relaying data, send or data methods encoded in stun header. Data attribute in attribute section. Removing allocation, refresh method with 0 lifetime, lifetime attribute equals 0, also in attribute section. ICE candidate checks, binding request plus special ICE attributes. It fits in the stun attributes perfectly. Everything matches the diagram. How the large Wireshark example fits the unified diagram. The big screenshot literally showing IP header, UDP header, stun attributes, message integrity, XOR relayed address, lifetime, bandwidth. This is exactly the unified diagram. They just expanded it in Wireshark. So how everything relates to the unified diagram. So the long text describes the protocol operations, concept, stun or turn methods, where it appears in the diagram, stun header, type, turn attributes, stun attributes section, message integrity, stun attributes of type 0x0008, XOR encoded address, stun attribute values, ICE priorities, controlling flags, stun attributes, channel bind, stun header, method 9, channel data messages, not inside this diagram. Use special 4-byte channel bind format. Everything except channel data fits perfectly. So the full stun turn packet structure diagram, realistic clean flowchart style. IP packet, we have IP header, SRC IP, DSD IP protocol, UDP 17 TTL to UDP diagram with the UDP header, SRC port, TST port length checksum. Then towards stan or turn message, request or response, we have stan header 20 bytes, message type, message length, magic cookie, transaction ID 96 bits. Message type equal method plus class, method equal binding, allocate, refresh, etc. Class equal request, success response or error response. Message length equal total attribute values not including padding. Transaction ID equal unique ID for matching request response. Stan or turn attributes. Each message may contain several attributes. Attribute header 4 bytes, type 16 bits, length 16 bits, value variable length up to 64 kilobytes, padded 232 bit boundary, padding bytes ignored, notes, length equals size of value only, value padded to multiple of 4 bytes, padding bits may be any value. Turn extensions, turn methods, message type 2 method field, we have allocate 1 client request relayed address, refresh 4 keep allocation alive, send 6 client to server data via turn, data 7 server to client data via turn, create permission 8 authorize traffic from a peer, channel bind 9 bind peer to channel number fast math. Turn defined attributes, examples, type 0x000C, attribute name, channel number, purpose 16-bit, turn channel ID, type 0x000D, lifetime, purpose allocation TTL in seconds, type 0x0012, attribute name, ZOR peer address, purpose peer IP or port encoded, type 0x0013, attribute name, data, purpose payload for send or data, type 0x0016, attribute name, ZOR relayed address, purpose clients assigned relay address, type 0x0018, even port, request even port plus optional next, 0x0019, requested transport UDP or TCP or SCTP selection, 0x001A, don't fragment, ask server to IPv for DF bit, 0x0022, reservation token, purpose reserve related relay ports. How this looks like in real world usage, we have browser WebRTC client, allocate request, turn header plus turn attributes. We have turn server that it was sent by the WebRTC. It allocates success response, contains ZOR relayed address. Then our client now has a relayed transport address. Third, create permission, authorize peer address. Then it contacts turn server. Fourth, channel bind, optional for faster data. Or it contacts turn server. Turn, send, or data encapsulated. These are stan messages wrapped in UDP inside IP. Then you connect to peer. That's how you connect directly to peer. Your packet stack stays the same throughout. IP to UDP to stan or turn header. 2 attributes, optional turn data. Interactive connectivity establishment. Given the large variety of NATs deployed and the various mechanisms that may be necessary to traverse them, a generic facility called Interactive Connectivity Establishment ICE RFC 5245 have been deployed to help UDP-based application hosted behind a NAT establish connectivity. ICE is a set of heuristics by which an application can perform unsoft in a relatively predictable fashion. In its operation, ICE makes use of other protocols such as turn and stan. A proposal extends the use of ICE to TCP-based applications. ICE works with and extends offer or answer protocols such as the session description protocol used with Unicast SIP connection establishment RFC 3264. These protocols involve an offer of service with an accompanying set of service parameters followed by an answer that also include a set of selected options. It is increasingly common to find ICE clients incorporated into VoIP applications that use SDP or SIP for establishing communications. However, in such circumstances, ICE is used for establishing NAT traversal for media streams, such as the audio or video portion of code carried using RTP or SRTP. While another mechanism called SIP outbound handles the SIP signaling information, such as who is being called. Although in practice, ICE has been primarily with SIP or SDP based applications, it can also be used as a generic NAT traversal mechanism for other applications. One such example is the use of ICE over UDP with Jingle, defined as an extension to the core Extensible Messaging and Presence Protocol XMPP. Ordinarily, ICE works to establish communications between two SDP entities called agents by first determining a set of candidate transport addresses that each agent might use for communicating with the other. Referring to figure 7.11, these addresses could be host transport, server reflexive, or relayed address. So it could be a host transport, server reflexive, or relayed address. ICE may make use of both stan and turn to determine the candidate transport address. It could use stan first and then turn as a fallback. ICE then orders this addressing according to a priority assignment algorithm. The algorithm arranges for addresses that provide direct connectivity to receive greater priority than those that require data relaying. ICE then provides the set of prioritized addresses to its peer agent, which engages in a similar behavior. So if it has a peer agent that engage in a similar behavior, it will provide the server that has the greater priority. Ultimately, two agents agree on the best set of usable address pairs and indicate the selected results to other peer. Determination of which candidate transport addresses are available is accomplished using a sequence of checks encoded as stan messages. ICE has several optimizations to decrease the latency of agreeing on the selected channels. So they also decrease the latency of selecting or agreeing that to make it efficient, which are beyond the scope of this discussion. ICE begins by attempting to discover all available candidate addresses. Addresses may be locally assigned transport addresses, multiple if the agent is multi-homed, server reflexive addresses, or relayed addresses determined by turn. After assigning each address a priority, an agent sends the prioritized list to its peer using SDP. The peer performs the same operation, resulting in each agent having two prioritized lists. Each agent then forms an identical set of prioritized candidate pairs by pairing up the two lists. A set of checks are performed on the candidate pairs in a particular order to determine which addresses will ultimately be selected. Generally, the priority ordering prefers candidate pairs with fewer NATs or relays. So again, that's the key, fewer NATs or relays, therefore greater priority. The candidate pair ultimately selected is determined by a controlling agent assigned by ICE. The controlling agent nominates which valid candidate pairs are to be used according to its order of preference. The controlling agent may try all pairs and subsequently makes its choice, called regular nomination, or may use the first viable pair, called aggressive nomination. A nomination expressed as a flag in a stan message referring to a particular pair. Aggressive nomination is performed by setting the nominate flag in every request. Checks are sent as a stan binding request messages exchanged between the two agents using the addressing information being checked. Checks are initiated by a timer or scheduled as a result of an incoming check from a peer, called a trigger check. Responses arrive in the form of stan binding responses that contain addressing information. In some circumstances, this may reveal a new server reflexive address to the agent because a different NAT is used between agents from the one that was used when candidate addresses were first determined using stan or turn servers. Should this happen, the agent gains new address called peer reflexive candidate, which ICE adds to the set of candidate addresses. ICE checks our integrity check using stan's short-term credential mechanism and use the stan fingerprint attribute. When turn is used, the ICE client uses turn permissions to limit the turn binding to the remote candidate address of interest. ICE incorporates the concept of different implementations. Light implementations are designed for deployment in systems that do not employ NAT. They do not ever act as a controlling agent unless interacting with another light implementation. They also do not perform the checks mentioned earlier as do full implementations. So the type of an ICE implementation is indicated in the stan messages it sends. All ICE implementations must comply with stan RFC 5389, but light implementation will only ever act as stan servers. I extend stans with attributes described in Table 7.4. Table 7.4 stan attributes defined by ICE, name, priority, value 0x0024, purpose or use, computed priority of associated candidate address, name, use candidates, value 0x0025, purpose or use indicates selection of candidate by controlling agent, name ICE controlled, value 0x8029, purpose or use indicates sender of message is controlled agent. Name ICE controlling, value 0x802A, purpose or use indicates sender of message is controlling agent. A check is a stan binding request containing the priority attribute. The value is equal to the value assigned by the algorithm described in section 4.1.2 of RFC 5245. The ICE controlling and ICE controlled attributes are included in stan request when the sender is the controlling or controlled agent. So these ICE controlling and ICE controlled attributes are included in the stan or turn attributes. Stan attributes respectively. A controlling agent may also include a use candidate attribute. If present, this attribute indicates which candidate the controlling agent wishes to select for subsequent use. So a use candidate will allows you to select what do you want next as a candidate, or what server you want to connect, or what peer. So stan or turn message, request or response. We have request, client to server, stan header 20 bytes, message type request, method plus class equal request, message length, magic cookie, transaction ID. So as you can see, the transaction ID is the same here for response. In response, we have server to client. Sorry, we need to go to request first. So for attributes for request, examples: username, realm, nonce, requested transport, even port, don't fragment, XOR peer address, %. Each attribute has its own type length value, padded to 4 bytes. Now for response, server to client, we have stan header 20 bytes, message type, success or error, method plus class equal response, message length, then magic cookie, then same transaction ID. Then we have attributes, examples: XOR map address, lifetime, XOR relayed address, then error code if error, then channel number, then data for data indication, then reservation token. Then we have type length value. Key takeaway: request and response have the exact same packet structure. Only message type and attribute differ. So only the message type and the attributes differ, but the transaction ID and the cookie has the same structure. Transaction ID must match so responses can be mapped to the correct request. Real network capture, example annotated like Wireshark. It's what a turn allocate session actually looks like. Actually, we have discussed this, or we have seen this already. Turn allocate request, client to server, frame S1 UDP 536379 to 3478. of turn. IP header source IP 192.168.1.18, destination 34.102.200.92. Then we have UDP header SRC port equal 56379, then DST port equal 3478. So after UDP header, we have stun or turn message. We have message type allocate request 0x0003, message length 44, magic cookie 0x2112A42, transaction ID 96 bits. Then we have the attributes. So we have username 0x0006, length equal 8, value equal client 01, realm 0x0014, value turn.example.com, nonce 0x0015, value 9F8AB874, etc. Then attribute requested transport 0x0019, we have value colon 0x11 UDP. Lifetime 0x000D, value 600 seconds. Turn allocate success response server to client, frame S2 UDP 3478 to 56379. Turn stun message colon, then we have message type colon success response 0x0103, then message length colon 36, then magic cookie 0x2112 A4A2, then we have transaction ID same as request. Then we have attributes. Zor relayed address 0x0016, then we have IP colon 35.201.94.22, then port colon 49320, then lifetime 0x000D, then 600 seconds, then Zor map address, then client reflexive address public IP. Turn data indication server to client, stun message type colon data indication 0x0117. Attributes, we have data payload forwarded from peer, then we have Zor peer address. This is how turn looks in Wireshark for WebRTC. Web app architecture diagram, turn or stun in WebRTC. Here's a clean modern system diagram showing how turn or stun fits inside the real web application stack. So we have WebRTC web app architecture, web app JS HTML/JS/WebRTC API. Then it call create peer connection to WebRTC ICE agent. It gathers candidate and sends stun or turn messages. Then we have host local candidate UDP LAN. And then we have another candidate stun server public IP discovery turn server relay traffic if not fails. Then we have signaling server WebSocket or HTTP exchange SDP. So after that we have stun binding rack request, then binding response to it, and then turn allocation rec, then allocate success relay IP. Peer-to-peer attempt first, UDP hole funching. If fails, use turn relay. Then here we see browser A direct UDP path now to browser B, stun succeeded. Or if direct fails, browser A to turn server to browser B, so relayed via turn. So part 1, detailed step-by-step packet evolution from allocate to create permission to channel bind to send /data. This shows exactly what the packet looks like, how the stun or turn message evolves, and what attributes appear at each step. Turn packet evolution full life cycle. This is exactly what a WebRTC browser plus turn server exchange on the wire. Step 1, allocate request. Client asks turn server to allocate a relay address. We have IP header, UDP header, stun or turn message. Then we have message type allocate request 0x0003. Then we have magic cookie 0x2112A4A2. Then we have transaction ID A1B2C3. Then we have attributes username client 01 realm turn.example.com nonce ABCD1234 requested transport equals 0x11 UDP. Lifetime equals 600 seconds. Even dashboard optional, don't fragment optional. Step 2, allocate success response. Turn server assigns a relay IP plus relay port. Message type colon success response 0x0103, then magic cookie same, transaction ID same. Attributes Zor relayed address equal 35.201.94.22 colon 49320. Then we have lifetime equals 600. Then we have Zor map address equal clients public IP colon port. Browser now has host candidate LAN IP, server reflects the candidate via stan, relay candidate via turn. WebRTC will now try to communicate with peer. Step 3, create permission request. So this is until step 8. So client tells turn, I want to communicate with peer X. Message type, create permission request, argument 0x0008. Then we have attributes Zor peer address equal IP/port of remote peer. Step 4, create permission success response. Message type, colon success response 0x0108, no special attributes. Permission is created in turn so the server allows traffic from peer. Step 5, channel bind request, optional but faster. Client bind peer's address to a 16-bit channel number to reduce packet overhead. Message type, colon channel bind request 0x0009, attributes channel number i.e. 0x4000, Zor peer address same peer. Step 6, channel bind response. Message type, colon success response 0x0109. Now client can send channel data frames instead of stan messages. Much smaller, lower latency. So this for channel bind, right? We discussed step 7, send indication, client to turn. If not using channel data, client sends via stan indicated send. Message type, send indication 0x0016. Attributes Zor peer address. You have peer address and data payload from DTLS or SRTP. Turn forwards this to peer. Step 8, data indication server to client. Turn send peer's data back to client. Message type, data indication 0xx0116. Attributes Zor peer address. For peer, data, ProWebRTC frame payload. So summary table. Step 1, method, allocate. Purpose, request relay, attributes, username, nonce, requested transport. Step 2, method, allocate success, purpose, relay, assign, attributes, Zor relayed address. Step 3, method, create permission, purpose, allow peer, attributes, Zor peer address. Step 4, method, CP success, purpose, confirm, attributes, none. Step 5, method, channel bind, purpose, bind to 16-bit channel, attributes, channel number. Step 6, method, CV success, purpose, confirm, attributes, none. Step 7, method, send, purpose, client to peer data, attributes, data. Step 8, method, data, purpose, peer to client data, attributes is data. So part 2, mega diagram packet plus flow plus architecture. This merges packet format, turn workflow, and WebRTC system architecture into one diagram. We have WebRTC, turn integrated mega diagram. We have web app, JavaScript, RTC peer connection or ICE agents or DTLS or SRTP. It will connect to ICE connectivity checks. We have available candidate, host, stan, turn candidates. So in host candidate, we have 192.168, etc. Stan server binding, public IP discovery, turn server relay, allocation or permission, signaling server ws/http/sip. Packet flow step by step. Step 1, allocate request, client to turn, IP header, then UDP header, then stan header, type equal allocate request, then stan attributes. In stan attributes, we have username, realm, nonce, requested transport UDP, then lifetime, then even port, which is optional. Step 2, allocate success, turn to client, stan header success, attributes, Zor relayed address, relay candidate, lifetime, then Zor map address, client, public IP. Client now has a relay candidate. Step 3, create permission, client to turn, stan header, create permission, attributes, Zor peer address, who client wants to talk to, Step 4, create permission success, empty success. Step 5, channel bind, client to turn, stan header channel bind, attributes, channel number, IE0x4000, Zor peer address. Step 6, channel bind success. Step 7, send indication, client to turn, attributes, Zor peer address, then data to DTLS SRTP, payload to peer. Turn forwards to peer. Step 8, data indication, turn to client, attributes, Zor peer address, then data from peer. Final connectivity result, direct path. If stan succeeded, browser A connect to browser B. Relay path, if stan failed, symmetric NAT, CG NAT. Browser A to turn relay to browser B.